Welcome to Maths with EJD. In this video, I'll be talking about multidimensional spectral analysis, still on the spectral analysis playlist. Of course, we've looked at different dimensions of spectral analysis. Now we are going the multidimensional side of things. All right. So, by way of introduction, spectral analysis extends naturally from one-dimensional signal. So you have one time series, one signal. Of course, I mean, we use data set, time series, signals interchangeably in this situation. So spectral analysis extends naturally from one-dimensional signals, e.g. time series, to multidimensional data such as images, videos, and multi-channel sensor arrays. The goal is to understand frequency content, correlations, and structures across multiple dimensions simultaneously. So and then we talk about the fundamentals of multidimensional spectral analysis, right? So by definition, we have extension of it's a multidimensional spectral analysis is an extension of Fourier analysis to multidimensional signals. All right. So we have applications. For instance, we can have 2D in image processing, talking about textures, patterns, and filtering. We have for 3D three dimension, we have volumetric data like medical imaging, geophysics, and we can have multi-channel where we can talk about things like multi-sensor fusion, hyperspectral imaging, and audio-visual signals. So the key challenges is that computational includes computational complexity, cross-dimensional correlations, and interpretation of spectral content. And then that takes us to the idea of two-dimensional spectral analysis, 2D spectra. So we have the mathematical foundation is such that we have the 2D Fourier transform defined as f of u v, that's double integral f of x comma y e raised by minus j2 pi into ux plus vy dx dy. And the properties, that's properties like linearity, symmetry, separability, and convolution theorem. All right. So applications for 2D in particular, we can have it in filtering. We can have it for low pass filters where blur or smooth images we can blur or smooth images by attenuating high frequency components. Then we can have high pass filters where for edge detection by highlighting abrupt changes. We can have band pass filters for texture or pattern extraction. Then we can use it for texture analysis. So of course, this whole thing is talking about images, right? So for texture analysis, we can detect periodic patterns like e.g. fabric textures, fingerprints. We can have Fourier descriptors for image recognition. Then we can use it for compression and restoration. So JPEG uses discrete cosine transform, DCT, a two-dimensional spectral method. So if you're working with pictures, images, and all that, this is really useful. Then we have noise reduction by suppressing noise-associated frequencies. Then we have that's for sound now, like music. And then here we have it is also useful for feature extraction, where we have spectral signatures of objects in frequency space, aiding classification. So the Python implementation, 2D Python implementation, we have this interesting code right here. So here we need NumPy, Matplotlib. Then we have a library called SkyMage, and from there we extract data and color. And then of course from NumPy we have fast Fourier transform, where we need the shift and FFT2. All right. So here we are loading a grayscale image. So we call that IMG. So from this data from SkyMage now, so we're saying data.camera, it's going to give us a particular grayscale image. And then we go for the 2D Fourier transform. So we have F, which is FFT2. I believe T2 should be for about 2 dimensions. So we have FFT2. F is equal to FFT2 of the image that we have downloaded here. Then we now say F shifted is FFT shift of F, this F here. Then we do the magnitude spectrum, NP log 1 plus absolute value of F shifted, right here. And then we can, run all of that. And we get, of course, every other thing is dimensioning this. Then we have two subplots, the original image in grayscale, and we have the magnitude spectrum also in gray. So if you run this, we see the original picture and the one we have transformed in 2 dimensions using FFT2. So watch out for that. Yeah, lovely. So finally, we have the original image. So this is the original image that we got from data.camera, right? And then this is the 2D spectrum, the 2D transformation we have carried out on that image now on that picture. So I'm trying to see if there's something I can tweak here. It doesn't appear that there's anything I can tweak to see if there can be some changes. Okay, I think that's about that basically. Right. Okay, so we move on to three-dimensional spectral analysis. So the foundations, the 3D Fourier transform is given as f of u of v, f of u v w, and that will now be a integral kind of thing now. So we have f of x, y, z equals, the kind of thing we had before, it's now 3 dimensions, basically. So the applications of 3D spectral analysis, we can have that in medical imaging for MRI and CT, which produce 3D data sets. Spectral analysis helps detect anomalies. In geophysics, it is good for analyzing three-dimensional seismic cubes for oil and gas exploration. Then in video spectral, we can also do video spectral analysis. So we can treat time as the third dimension. So we have X, Y. So it's 2 dimension plus time, making 3D in that case. So for video spectral analysis, and it's used for motion detection and event recognition. Then we can also use it for data compression and denoising. So 3D wavelets for volumetric data reduction can happen. So let's do a 3D implementation, just like what we did previously. So here now we simulate a 3D signal that is cube with sinusoidal pattern. So here we declare our X, which is like the signal in this case now. Okay, we declare an X, right? So we NP line space between 0 to 1, and we have 64 equal division. So for X, Y, Z, we have NP dot mesh grid, that's XXX, because we're dealing with a cube. Then the signal itself is 10 times 2 pi X. So that's the X we extract from this component, plus NP cos 10 times 2 pi Y. Of course, that's what our signal looks like in this case. So we now have the 3D Fourier transform. So in this case, now we have F3 equals NP.FFT.FFT, and so that's like 3-dimensional now. Then we take the signal, and then the magnitude is NP.log 1 plus absolute value of that shift, that F3 we have up there. The fast Fourier transform shift, and then we show the central slice, by running this now. So we use CMAP Inferno. So of course, we can change that map. So it's Inferno here. One particular CMAP I like is what is it now? Rainbow. So this also gives us this. So we can try different things. We can also do like greens. Okay, we can do greens, something like this. Yeah, so whatever you want, you can go for it. Let's do like red and see what it looks like. Okay, this. So, but I think I like Inferno. Let's leave it as Inferno like that. All right. So that takes us to multi-channel spectral analysis. So the concept is that data contains multiple channels or signals, e.g., we can have hyperspectral imaging, where we have hundreds of bands across electromagnetic spectrum. Then we have EEG, MEG brain signals across electrodes, and we have audiovisual sensor arrays like that. So we can have the methods, right? So we have cross-spectral density. I think we did a video on cross-spectral density. I think that must have been the 17th video, right? Cross-spectral density for correlation of spectral content between channels. Then we have multivariate spectral estimation. So we have multi-channel ARMA models. Then we have principal component spectral analysis for dimensionality reduction with spectral preservation. So those are some methods for multi-channel spectral analysis. And it has applications in remote sensing for land cover classification using hyperspectral signatures. Then in biomedicine for spectral coherence between brain regions. Then it's good. It's also useful in communications where we have multi-antenna like MIMO systems analysis. I think multiple in, multiple out, or something like that. I believe that's what that is in telecommunication. All right, so we can talk about the Python implementation also, multi-channel Python implementation. So here we have, so from scipy.signal import cross-spectral density, right? So we simulate 2 channels which are correlated signals. We have a sampling frequency of 500, then T is from 0 to 2 divided into 1 over Fs equal portions. Then we have the first signal, that's sine 2 pi 50 2 pi 50t, of course, we get sine from numpy. Of course, we plotted numpy previously. Then we get pi from numpy also. And then we have this random length. Now, this is some kind of noise. And then we have signal 2, that is 2 pi 50t. Then we have a phase added to it. Now, that's pi over 6, right? With some noise also added. Then we have the cross spectral density. So we have pxy against the frequency, and then we get CSD, signal 1, signal 2, Fs equals Fs. Number per segment is 256. And then we plot we did say plot the semi-log y, if you like, FNP, absolute value of pxy. And that's the cross spectral density between channels. And on the x-axis, we have the frequency in hertz, and on the y-axis, we have the cross spectral density magnitude. And if we run that, this is what we get. So this is cross spectral density between channels, right? Now, finally, we have the challenges and future directions, right? So talking about high dimensional complexity. So it requires advanced algorithms like fast Fourier transforms and tensor decompositions. For interpretability, we need spectral features across multiple dimensions, which can be difficult to map back to physical phenomena. Then for machine learning integration, we can do deep learning with spectral domain representations like CNNs using spectral inputs. Then for quantum spectral analysis, we can have emerging frameworks for multidimensional signal representation. And with this, we come to the end of multidimensional spectral analysis. So you can do spectral analysis not only in 1D, you can do it in 2D, 3D, and you can also have multi-channels, right? All right, so if you want, let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, thank you so much. If you haven't, you know you are missing a lot, so you don't want to keep missing. Go ahead and subscribe, right? After subscribing, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And that's not the end. You can take it a step higher. You can become a member of my channel, and that gives you some special privileges. Just click on join, and you see those 3 levels of membership, like that. So at the very highest level, we can actually have one-on-one conversations on any topic you choose, maybe maths or data science or scholarships, personal development, anything that you think I talk about on my channel, we can actually discuss those things like that. All right. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. So like come away again, keep doing Python right, keep doing data right, keep doing maths right. Bye.